All right, how's it going, everyone? Just gonna check in with Calgary. If the audio is working okay for you guys, just let me know. How it has midterm projects been going so far? How has this switch from kind of being a solo developer to working in a group been? It's a bit of an adjustment, but is it going good so far? Yeah. Cool. So today we're going to be looking at user authentication again. We had a bit of exposure to this when we were doing Tiny App and we had users logging in, and we learned a few things around authentication back then. But we're going to revisit and kind of explore and see what areas we can look into further with this. User authentication is a huge topic. It's something that people specialize in and devote full careers to, but we're going to try and see broaden our scope on what we know. But before we look at anything new, let's try and review what have we done so far. So I know for Twitter, we didn't really implement user login. Maybe we looked at it as part of a stretch. But if we think all the way back to Tiny App, so a couple of weeks ago, what did we do for storing passwords and sensitive data? What were the approaches we had for these things? So we had hashing, and part of that was salting. What's a hash then? Sure, yeah. Yeah. So we. Mm. Cool. So we said that hashing is a way to take a set of info or data and convert it into a fixed length, say string, and that conversion is kind of one way. We can convert it into the string, but it's near impossible to take our hash string and move it back. The other thing that we wanted to be met was that if I hash maybe a string dog and it gives me a set output, I don't want any collisions, or very few if I can help it, on any other words that I put through my hash. And salting was an extra step we did when we were hashing. Does anyone recall why we added salts, or what a salt was? Yeah, so salt is an extra characters that we add to our hash so that it's even harder to break the hash system that we have. If we store all our information in hashes plus a salt, they're even more obscured. So what did we do to authenticate someone? In Tiny App, when we were logging in our users, what were the tools we used for this step? So if you remember, there were a couple things we did when we were communicating from our server to our client, when we were sending maybe passwords, or when we were. How did we make sure that our server knew someone was logged in? What was the thing we used? Yeah, we used sessions, and sessions was kind of the second thing we used, and before that we had cookies. So just as a review, cookies is a set of storage client side in our application. So it exists in the browser, and with our web applications, we can set and like modify or remove cookies from our server or from the front end to store any helpful information that we wanted. So in TinyApp's case, we used cookies initially to store user IDs so that we knew what user was logged in and when they were logged in. And then we moved to sessions. And sessions, does anyone remember what was the difference between cookies and sessions? Why were sessions a bit more preferable? So the comment was that sessions are dynamic, that they're generated when a user visits the site, and part of the reason they're like this is because the data with sessions is actually stored server side. So if we have our server here and we have our client, with sessions we have a whole area of storage on our server. So this is our server, and this is our client. I'll just do CL. And on the front end, all we're storing, we're still using cookies, but we're storing a little like number that references what part of the session we're using. So our client, has this number 12, and then when our server communicates with it, it looks in its session storage, looks in here, and it finds the session, maybe with number 12, and all the information associated with that user is, stored right here. So it's safer in the sense that we're not storing any sensitive data on the client side. Client side is more public, is easier for people to get a hold of. All of our session information is stored in the back end. We have a little tag or like access number that gives everyone access to the session, or not everyone, sorry, it gives the correct user access to the session, but the data never actually enters the client side of our application. Nice. Any other things people remember from TinyApp that we might have missed, things that were important to do when we were implementing passwords, when we were implementing authentication? Any best practices or things we should be careful with when we're doing these things? The one comment was encrypting the data. So encryption, yes, that is another important thing, and it's something that we're going to be focusing on a lot in today's lecture, actually. Okay, if there's, oh nice, and Danny said from Calgary that the session will time out. So we have our session storage on our server side, and sessions also have a kind of a lifespan. After a certain amount of time, they just, not the whole session, because there's always reserved space for the server session, but a user specific session will just get thrown out if it hasn't been used at a certain time. You'll just cross off that line of the session, cross off this one, and in that sense, users using your application for a bit, after they log out and they're inactive for a while, that sensitive information doesn't last forever. It just gets tossed away. I think there's a lot of terms in user authentication and in security in general, so we're going to try and clarify just a couple before going any further. So we have this authentication versus authorization. So maybe two similar words, but the authentication is the process of confirming someone's identity or proving that you are a specific user. So if I'm logging into Facebook, when I log in and I use my email and password, I'm trying to authenticate that I am in fact Travis and I have access, or that's all I'm trying to do, is that I am Travis. The authorization part of the logging in is granting correct access. It's verifying that you have the correct access to see or get things. So when I'm logging in to Facebook, I first authenticate that I am Travis, and then Facebook decides what content I get to see based on that, and that's the authorization part of things. So if I'm able to go and upload photos or edit my page, that's because I've been correctly authorized to see the right content, to view the right things. And these things are usually implemented together, but you can have cases where you implement one correctly and you fail to implement the second one. So I can have the case where I am correctly logged into a site, so I have proper authentication, but somehow when I'm navigating the site, I get access to maybe an admin page, and I can like delete stuff, I can like edit things when I'm just a normal user. That would be a case of correct authentication, but bad authorization. We're correctly identifying that it's me, Travis, but we're giving me bad access in some cases. So we have to think about both when we're building our web applications, when we care about what users can do which things. The other two terms that can be very similar are encoded and encrypted. So encoded is when we transform data into another format using a scheme that is somewhat widely available, and the purpose is so that this data is in a usable state. When you encode something, it can usually very easily be switched back to its initial form. Both encoded and encrypted stuff can look very similar. So I could have just a big string of characters, and that could be my encoded thing. And I could have another string of characters, and this one could be my encrypted thing. The difference isn't in how they look. The difference is in their purpose and how easy it is to switch back to their real meaning. So with encoded, very easy to switch back, and its purpose isn't to be secret. Its purpose is to be usable. So sometimes when we do like UTF encoding, it's more usable for certain programming. Encryption, however, transforms the data into another format in a way that only specific individuals can reverse the transformation, and its purpose is to obscure data. So encryption is the idea that I want to keep this information secret. It's maybe sensitive, it's something that I only want to know and someone else who I give the authority to know. I lock the data down, and I don't want anyone who looks at it to be able to know what it says unless they have the correct tools to unlock it. So encryption for secure stuff, encoded more for usability. But how do we encrypt? So we always talk about, well, we'll send it encrypted, we'll do these things. But let's try and look at actually how we use, different methods of encryption. So the first demo we're going to look at is I have a method of encrypting something, and I'm going to send it to the Calgary cohort. And Calgary, if you can use this cipher and maybe decide on one person to input into the Vancouver Slack channel, I'm going to ask a couple questions on the monitor, and you guys can give your answers. For us here in Vancouver, just for the little time being, try not to look at the Calgary Slack, and we'll see if we, as a group in Vancouver, can try and see what the pattern that Calgary is using. So Calgary, the thing I just gave you, we can see the top row switches with the bottom row, and the bottom row switches with the top row. Okay, so now me and Calgary are exchanging messages. I give them this number. So to us here in Vancouver, this doesn't really make a lot of sense. But through the lens of Calgary's knowledge, they can decrypt this number maybe to give some meaning. So whenever you guys work that through the information I gave you, just give us a message in Vancouver to let us know what it should be. So for this encoding, we're just using numbers. Oh, so Greg put it in the Calgary chat. I'm just going to copy and paste that into the Vancouver chat so you guys can see as well. So this first one, we had 10/31/2019. So this number is not making much sense to us, but when they've encoded it, we get this, which is kind of like a date string. So maybe, I'm trying to communicate. Could be. We have another example. We'll see. So this one is the time. Let's try and see what Calgary comes up with this one. So they got 107. So the comment here is that we think the encode is that we're adding 5 or modularly adding 5. So when we get to 9, we're rolling over. All right, that seems like it's probably the right thing, but we'll do one last thing. So this one we have this string, and we kind of know that the letters might stay the same, but the numbers are going to be swapped. There are some Vancouver side we might have deciphered this one. Yeah, so Calgary says that it's this phrase. So it would kind of like leet speak for eat candy. So maybe this code is pretty easy, but we had a little bit of a message that we could send through. So we're saying, Halloween at 107, maybe we were going to eat some candy. So this was the cipher we were using. When we have 0, we're swapping it with 5. These get swapped to the bottom, and the bottom gets swapped to the top, which essentially the comment was we're adding 5 to the number modulo, so that if we're adding 4 to 9, we're carrying back over or if we're adding 5 to 9, we're carrying back over to 0, 1, 2, 3, and we're getting to 4. So with numbers, maybe that's like pretty obvious, but this is an adaptation of a cipher or an encryption known as ROT13. But what are some disadvantages, or what are some problems with this cipher? I mean, one, it was broken by our second question, so it's probably pretty predictable. What could be another disadvantage of this type of cipher? Sorry? Yeah, so it was only working for the numbers. This is maybe a better cipher that we could have used, called ROT13. So it's similar to this number one we used. Here we have the first set of numbers is shifted. So we split the numbers in half, and we have the first half shifting to the second half. Same with the letters here. We have our first 13 letters being shifted, 13 down. We're adding 13 to the letter, essentially. So given a set of text hello, we get this encoded thing down here. This is an example of a broader set of ciphers called Caesar ciphers, and it was actually first done by Julius Caesar to encode messages during different battles and to just like send secret things. So pretty old, and for a long time, like ROT13 was pretty secure. Like people could send messages and people wouldn't know. You can also do this type of sliding cipher where the amount you slide varies. So here we're sliding our numbers or our letters by 13 steps. You can do a slide of 2, so A becomes C. And every message we send, we could slide our letters by different amounts, maybe making it more secure so that if someone figures out on one of our messages that we're doing a sliding window of 13, the next one we switch it up and we do 6, then we do 5. So before computers, maybe a bit secure. But there's some problems. You can eventually see the pattern. With our number one, we saw the pattern really quickly. The letter one, it probably would have taken us some more time, but it's pretty predictable over time. And the other problem with this type of cipher, or with any type of encryption really, is that you need to communicate how to use the method securely. If someone intercepts the ROT13 explanation, then your encryption doesn't work. In order for me in Calgary to have started communicating with this cipher, I had to message them in Slack and say like, oh, use this thing. If any of you guys had just looked in like the Calgary Slack, you could have seen it and like broken our cipher. There needs to be an initial way for us to like agree upon how we're going to secretly communicate, and that's a vulnerable point. If someone's listening in, if it gets intercepted, then our cipher or our encryption is pretty much useless. So although this ROT13 or the number one was really weak, it still is an example of an encryption because our purpose was to obscure the data. We weren't doing it for like, it's not easier to read when I give you some weird numbers like this or something. It was so that our stuff was hidden. And now we're going to look at some like broader vulnerabilities that can happen with authentication. So the first area is when our communication is in transit. So we've looked at HTTP methods. We've looked at HTTP communication where our front end, our client, is sending a request and then our server is sending a response back. That message just doesn't instantly appear at our server. It actually has to physically travel from our computers to wherever the server computer is. And that'll be over maybe like Wi-Fi as a medium for a bit. It might be over a physical Ethernet cord. There's all this stage in between. And there's ways that sneaky hackers can intercept this data. So there's like packet sniffing. Packet sniffing is the process of like physically putting a little reading device on a wire somewhere, and it just like reads the signals coming in and out. So people have used packet sniffing for if me and someone are sending a message, they can in between be secretly listening in. Spoofing. Spoofing is a way of the messages are going from one IP to another. If I pretend to be someone's IP, I can intercept messages as well. Another vulnerability is a data breach. So all of our stuff stored in a database. In Tweeter, we stored all of our things in a relational database in Postgres. If in Tweeter we had stored our password information there as well, and someone had gotten to our computer and was able to download the whole database, that would be a data breach. That might be a physical data breach because they got in directly to where the data is stored. But we could also access that data through other ways. If I know your password or security information, I could probably remotely get into your database that you store on your computer. If a big company stores all of their data on a cloud hosted database, similar things can happen. We can also willingly give up our data. There's a big area of this called social engineering. That's the idea of convincingly or creating situations where people are likely to reveal sensitive information. Social engineering is like the idea of befriending someone and like, hey, what was your mother's maiden name, or what did you want to be when you grow up? You're mining data. You're trying to get enough information about someone so that you can use it to maybe break into their Gmail with your confirmation questions. There's also stuff like phishing. Phishing being those obviously fake emails that go around to everyone saying your social security number has been leaked. You need to do a reset password and this and that. And they send it to thousands of people. Some people get tricked and they get information. After maybe one of these other vulnerabilities has been taken advantage of, people can then impersonate you. They can go into your different accounts and get even more information. But we're going to look at a couple of these vulnerabilities through an example and see what solutions or what methods there are to make it harder for people to break our authorization, to break our security of our web applications. So the case we're looking at is we have two people, Bob and Alice, and they've just launched their new startup. It's a web app called StringCan. StringCan is a messaging app created to send secret or confidential messages from one person to another. They're a little late to the game, but they're doing it nonetheless. During testing, Bob and Alice find out that some of their secret messages have been leaked online. They're appearing online. After some investigation, they find that Sneaky Eve is using a packet sniffer to intercept their sent data. So what it says, the solution here is to make it so the data is, if the data is intercepted, it can't be easily read. And what's our main method of doing that? How are we going to stop Sneaky Eve from being able to just read all the data that she's intercepting? So the comment was, could we use a public and private key? Yeah, that's something that we could use, and that's like a method of encryption. To start with, so encryption. But how do we encrypt? Public and private keys is one way of doing it. The method that we're going to look at right now is just a single key encryption. So, but as a summary, a key is usually a random string that is used with encryption algorithms to encrypt data. So if I have an encryption algorithm and I have some data, I can use a key and I'll get some encrypted data. The good benefit of using keys is that in order to decrypt this encrypted data now, I need to know both the algorithm and the key that was used to encrypt it. The comment was public and private keys. That's an example of asymmetric keys or asymmetric encryption. This is an example of symmetric encryption. So in symmetric encryption, we have one key that encrypts and the same key decrypts. So it's very important that this key is secret. If this key gets out to people, then anyone, our data is no longer encrypted because anyone can decrypt it. The key makes it so that I can uniquely lock and uniquely unlock the data. Is this part, are we good on this step? Keys are just like a random string essentially, and they're appropriately named keys because they're just like a lock. They're gonna like lock stuff and unlock stuff. If I want someone else to be able to read my encrypted data, I am going to have to pass them the same key. So this is a similar problem to our cipher. In order for Calgary to start deciphering my stuff, I needed to pass them my encryption method. If we were using a symmetric encryption, I would have to pass Calgary my key, and that's a vulnerable state. How do I pass Calgary? How do I pass the person I want to share my data with this secure key, this secret key? Because once they have the key, if I have the key and Calgary has the key and no one else has seen it, we can pass data back and forth all day very, very securely with this symmetric system. So here's our challenge. We're going to take a break for you guys to think about this, but when we come back, we'll see if anyone has ideas on how to solve it. But here's our situation at least. I have a box, and I have 2 locks. This box can be locked with either of these locks, and we're going to have 2 people, and our challenge is to be able to pass the key or the combination to one of these locks to another person via a delivery service, so like a post office or something. And we want to make sure that the post office at no point during the delivery can open the box and just like get the key, get the code in this case. So this is mimicking our key encryption thing. We have a server that has an algorithm and a key, and we want to give that key to another server, another person. We can do this just with 2 locks. Our one person has 1 lock, and our second person has the other lock. And there's no restrictions on how many times you pass the box back and forth. The only rule is that if any point I'll be delivering the 2 things, I can find the key of the lock, then you fail, I guess. So think about it. Well, first, is that kind of clear? Do I need to clarify the? Yeah, I'll give you the code to each of these locks, and they'll serve as the key. I'll put them on a piece of paper, and you can have as many copies of the key that you want. But the idea is you are able to put that piece of paper with the code on it inside this box if you want. I mean, you could just get me to send it as a piece of paper, but obviously I would read it right away. So yeah, any other clarifying questions for that one? Nice. We'll break for 10, 15 minutes. Let's say we'll come back at 9:55. Also, Calgary, if there's any clarification on activity, let me know in the chat. You guys can also give your suggestions on how we can do this when we get back, and I'll get a couple of us here to enact your solution as well. Like, where did my... Oh, yeah. So, what was the question? So this is locking the box, and then I lock this with this one, with this key on it. And but the key, is it the key to the second lock or the first lock? Okay. Yeah. It's okay. We can try it. But the other thing to think about is this. Like, I can't actually lock this box, unfortunately, but this is my space to unlock the box. I can, and any physical options you have are available.
So could I attach like the outside? So
Yeah.
and you have to, and the key has to be unlocked in order to be used. I lock it.
Sorry, what's the question?
I lock out of the box. That you can't.
If you lock the key on the outside, like I'm gonna make some tags, like I'll just be able to read it. You know what I mean? All right. Did anyone have any ideas with our problem? So I'm going to re-explain it again, hopefully a bit better than I did the first time. On the left, we have one combination lock, and we have the key. We have the numbers to unlock the lock. On the right, we have another lock and another key that we have the numbers to unlock the lock. Somehow, we want to get this key from person 1 to person 2. So at that point, they can just send this box with the lock on it. From here, it's secure. Person 2 knows the code, they can unlock it, open the box, and get any of the data they need. They can also lock it with the same lock and send it back. So that's the scenario we're going for. And the tools we have are the lock and key on this side, and the lock and key on this side, and our box, of course. Any thoughts? I think yeah. You can do it if you want. Yeah, yeah. Okay, yeah, come on. I mean, we'll give whatever you're thinking a try, and we'll see.
Is there there's a message or something in the box?
No, you can put these, or you can put anything you want in the box. Yeah, but I'm the one who has to deliver it between you two, so. Okay. So.
No, I'm locking it and sending it back. Is this put on?
It, like, yeah. Okay. Yeah. Yeah. Yeah.
Now I'm opening it and looking at it. That work?
So that's the method, but the way you guys did it, every time you're sending data, you'll have to do three passes. So how can you do that same thing, but using the keys so that after you do one data pass, then you can just do single data passes?
Put your key in.
Yeah. Okay. Yeah, let's try. So we have this lock's key inside the box, and the box is locked. I can't get at it.
Yeah. Can I put this in?
No.
Okay.
But just let's continue like the same. Okay. So then we come back, and there's kind of, and then you send it back.
Now I can look at this key and store it.
Yeah.
So I have access to both blocks, and then I can send like this.
And then you would do another 3, but the other option is like at this point.
But he still can't, like, could he store this? Like,
Yeah,
or it's
yeah.
just like, so
He knows the password. Now you know the password, and you could, if you wanted to, just send the box back, and then from this point forward, for any things, you can just use the one lock because you both have the stored key. Cool. Good job, guys. That was awesome. So that's one illustration, and the algorithm that we just worked out is called the Diffie-Hellman key exchange. Oh. Let's see. This is another illustration of a similar way of passing the keys. So in the version we just had, we had 3 exchanges. We had from person 1 to person 2, back to 4, I guess. No, 3. Person 1 to 2, 2 to 1, and then back to 2, and then both people had the key at that same point. This is just an alternate way of doing it, where you do simultaneous data passes, and you only need to do. Oh yes, sorry, Kogi. So this is like another way of doing it. So in this example, we have a common paint that we share, so like yellow, and we both have a secret key. So this case we have orange, and on the right we have green. We combine the common paint with our secret color to get a public, like encrypted paint, and then we pass that to the other guy. So I pass this beige, and then Bob passes me blue. And then we combine the public transport, the encrypted one, with our secret color again, and we get a common secret color. So on the left and right, we have this like ugly green-brown color, which is a result of like green, orange, and yellow. In this example, the assumption is that adding colors is super quick, but subtracting colors takes like an eternity. So when I've combined yellow and orange, I can do that really quick to get this beige color, but I can't subtract the common color because I know the common color from beige to get orange, because that operation is very expensive. And that's how they do a lot of encryption values or encryption algorithms. They have, one operation that's very fast. In our method, we're thinking of addition, and then another type of calculation that takes a long time, so that it becomes a one-way encryption. Yeah, this one, you can look at the notes later and maybe break it down. The key exchange that we used here is kind of a more physical way of seeing it, although more steps. So back to Alice and Bob. They're still working on StringCan. They've now added encryption to their messages, and they're using Diffie-Hellman exchange so that they can securely pass the key, and they have this shared secret key so that all their messages are safe. But after encrypting this, Alice gets a message over StringCan from Bob. It says, "Hey Alice, quick question. What was the name of the high school you attended? Good job on the encryption, by the way. Also, Sarah and I were just talking, and we couldn't recall your mother's maiden name." Always trustful Alice responds, and she's like, "Hey Bob, weird question, but it was Harry Herbson High School. The encryption was hard, but now Sneaky Eve won't get our info. Oh, and tell Sarah it was Smith." So then later, she meets up with Bob in person, and she's like, "What was that weird message you sent me?" And Bob just has no idea what Alice is talking about. So they look into it, and they see that Sneaky Eve has struck again, and she has been spoofing Bob's IP to send fake messages. So in our first example, our problem was that our message could be read and easily intercepted if it was taken. Now Eve can't intercept our message, but what she can do is she can pose as, say, person 2. She can initiate that three-way handshake that we just had, that box pass back and forth. She can say, "Hey, it's me, Bob," and then I send her my private key. She locks it, does the same kind of example that we just saw, and then we both have a shared private key. And then we start sending messages, and our messages are encrypted. No one besides me and who I think Bob is can read those messages. But the problem was before that, when Eve has kind of pretended to be Bob right at the start. Yeah, so by encrypting the message, we know all conversations were secret, but we were not able to ensure that we knew who the secret conversation was with. So with our encryption, we know it's secret, but I don't know for sure who I'm talking to. The different options we can have here is we can have secret conversations with someone who you can't identify. You can have a public conversation where you know for sure who the other person is, or you can have a secret conversation where you know for sure who the other person is. So this third option being the kind of preferred one. We want to be secret, and we also want to know that I'm definitely talking to Bob and not someone else. So to get around this solution, the first thing we need to look at is public and private keys. This won't solve our problem right off the bat, but it's our first building stone, or stepping stone and building block. With public and private keys, Alice will have a private key and a public key. and Bob will also have a private key and a public key. Anyone who's communicating each other has a pair of keys. The way of thinking of public and private keys is kind of like a mailbox. The public key is like the location of someone's mailbox, and the private key is that person's own key to unlock their locked mailbox. I release the public key to everyone who I want to be able to send message to me. I say, you can send me, a mail at 123 Street, whatever. And so now everyone can send messages to me. But once I get the message in my mailbox, no one can, read them but me, because I have my personal key. I unlock my mailbox and I can see what mail everyone has sent to me. In this example, we're assuming that the mail delivery service is 100% secure. So in order for this metaphor to work, the people who are delivering my mail, they're like, bulletproof, like very trustworthy people. The main example of this like public private key encryption is RSA. I'll give you some articles in the notes to like look up on RSA, but we're just going to look at kind of the more theoretical ideas of public and private key instead of looking at the actual like math behind RSA. So this method is nice. It's a little faster for exchanging messages. Instead of having to do that back and forth, I can just send person A my public key and they can send me their public key, and now we can kind of communicate securely. But it doesn't help with our authentication problem. It doesn't help me to know for sure who's sending me my message. If I give you guys all my mailing address, you can pretend to be someone else. You can be like, hey, this is Bob, and here's my message, and you can send it to me. It'll be encrypted, like I'm the only one who can open my mailbox and read it, but you could have pretended to be anyone. I don't know for sure that it was you who sent me that information. So to get authentication, we need to use signing or certificates. They're kind of the same thing. So a signature is used to confirm the identity of someone, and it has to be used with a public-private encryption, asymmetric. So our first example, when I have one key and Bob has one key, that's called symmetric. When I have two keys of public-private and anyone else has two keys public-private, the mailbox thing, that's asymmetric. So we're going to break down a couple rules first. So we have Bob, and we have Alice. Our symbol for public key is this orange key, and our symbol for the private key is this kind of black spooky key. The obvious thing is if I take my public key plus the RSA algorithm and a message, I get this encrypted message. So that looks like this. And then if I take my private key and I use that same RSA algorithm and the same encrypted thing, I can decrypt it and get the message. So I use my public key to encrypt it, and then I use my private key to unencrypt it. But the cool thing with these public-private encryptions is the reverse is also true. I can use my private key to encrypt something, and then my public key will unencrypt it. So in normal message sending, this is the useful one, because I'm keeping my private key, I'm not telling anyone, and I'm letting you encrypt your stuff and send it to me, and then I can like read it. This one, just for normal communication, isn't really useful, because the only thing I can do here is I can encrypt messages and then send them to you, and then you can use my public key to see what I said. But because my public key is public, anyone can see what I said. But there's a trick in combining these two where we can get this certificate thing going. So if Alice wants to send a secure message so that Bob knows that it was her who sent it, first she's going to create a signature. So in this case, our signature is maybe just this string with the word Alice in it. And she encrypts it with her private key. So we have Alice's private key plus her signature. We get Alice's signature. This is encrypted with her private key. Second, she writes her note and she appends the signature to the end of the note. So this could be just, again, like a string, and this is like another string, the encrypted string. So she concatenates them together. Then she encrypts the combined note and signature with Bob's public key and sends it to Bob. So she has this. It's like any message she's wanting, or any note she's wanting to send. Hey there, Bob, how are you doing? Plus her signature. She encrypts it with Bob's public key, which she has available because Bob sent it to everyone. And so now she has the message or the note plus her signature. Oops, this got a little bit jumbled. There we go. So our end result is Alice's encrypted signature with a note encrypted by Bob's public key. Then she sends it. She sends her encrypted signature with the note encrypted by Bob's public key. So then Bob gets it. First, he decrypts the whole incoming message using his private key. It was encrypted with his public key, so he can use his private key to decrypt it. And because he is the only one with his private key, he's the only one who can decrypt it. So as a result, he gets the note and he gets Alice's encrypted signature. So at this point, he can read whatever Bob has sent to him, or Alice has sent to him. Like, hey there, Bob, how are you doing? He gets that note. So the encrypted message part is checked, but at this point he doesn't know for sure that it's Alice. To know for sure that it's Alice, he has to do something with his signature. So he uses Alice's public key then to decrypt her signature. So this signature was created with Alice's private key. He has her public key, and so he decrypts it and he gets her signature. The signature reads Alice, and Bob knows that Alice did send the message because only Alice could encrypt the signature with her private key so that her public key would successfully decrypt it. So if Alice hadn't written Alice and encrypted it with her private key, when he goes to decrypt it with her public key, it would just be gibberish. If it makes any sort of sense, if it says Alice, if it says any like hidden message, that means the only way he could decrypt it successfully is if she had encrypted it successfully. And the only way she could encrypt it successfully is if she used her private key to get to this stage. We'll just kind of go through that one more time because I know it took me a while to get the flow of things, and it might not be the easiest to look at it in this format and make sense. But when I send you the notes, if you look at the breakdown, it'll probably start to be a little bit more clear. But again, our first step is Alice creates a signature with her private key. She adds that signature to any note she's going to send to Bob, and she encrypts it with his public key. We get the full message that's being sent to Bob, encrypted with his public key, and inside that message, we have the encrypted signature from Alice. Bob gets it, and he decrypts it with his private key, getting the information from Alice and her signature. He then decrypts Alice's signature with Alice's public key, which is publicly available, and he gets the resulting signature, which he hopes should read something that makes sense. It should read Alice. Seeing that it successfully reads Alice, he knows that this message was definitely from Alice, and he knows that it was encrypted so that only the two of them could read it. Yeah. So the question was, Bob needs to know beforehand what Alice's signature would be. So he needs to know that she's signing it with the word Alice. Actually, kind of no. Because as long as Alice puts something in here that's like a straightforward readable thing, like she could have a string that says, hello, this is Alice. She's encrypting it with her private key, so it becomes just a jumbled mess of letters. And then on the other end, Bob is decrypting it with her public key. So here he's using her public key to get it. If someone else is trying to spoof that signature and they run it through with some key that they used, they'll get a jumbled set of letters. And then when they decrypt it with Alice's public key, they'll also get a jumbled set of letters. The only way this decrypt with Alice's public key will be something legible is if it was encrypted with Alice's private key. So you're ensuring that whoever sent the message used Alice's private key. Yes, so the question is, we're decrypting her signature with Alice's public key. How do we know Alice's public key is her public key? Well, the idea with is Alice's public key. Like you can go to Alice's page, you can go up to her and say like, "What's your public key?" She says it to everyone, so you can relatively sure know that Alice's public key is Alice's public key because you can just ask publicly what her key is, and she can tell it to everyone. And like if someone tells you, "Oh, Alice's public key is 1937," you can just like look on the application or look publicly and see if it matches that. If it does, then it's her public key. Yes. Yeah. So the comment was if you're not doing like verification of Alice's public key, like you're getting it from one source and you're just assuming that it is her public key, you could run into troubles there. In order for private public keys to work, the public key, you want to be like broadcasting it as widely available as you can so that everyone, there's no like doubt as to what your public key is. If you only give your public key to certain people, then it kind of actually makes it less secure because then it's easier to pretend that, someone can pretend that your public key is something else. Whereas if you're very loud and obnoxious about your public key, it's pretty hard for someone to come up and say like, "Oh, Travis's public key is something else." Yeah, if this is a little kind of strange, I encourage you to look at it in the note format. It might help a little bit. But the whole purpose is that now we have the message encrypted and we know for sure who is sending it to us using this signature, using the certificates. So fresh off of implementing RSA security, Alice and Bob get news that their database has been breached by Eve, and she's used the information she got from Alice. So she knows Alice's high school and mother's maiden name. Maybe she does a password reset on their database, and she gets all of the information. However, this time they think that they're prepared. They don't store any of the message history in their database, and all of their passwords have been hashed. They breathe a sigh of relief. But later, Bob checks his banking app and he sees that he has sent $100 to Eve. Remembering that he used the same password for both StringCAN and his online banking for some reason, he realizes that Eve has somehow decrypted the hashed passwords. But how? Any thoughts? Does anyone know how you would, if you break into these guys' database and they have passwords that are just hashed, how you would be able to maybe decrypt, say, Bob's password? So what Eve is using is called a hash table. So the steps to making a hash table is we have to think of what are the most common passwords. We'll make a list of them, And then we run this list through the common hashing algorithms. When people hash passwords, they're not secret algorithms. They're like usually very widely available. Then we compare our data breach to our new list, and we'll see if we can match with someone's hash password. So let's give that a try. This is our hash password. We know that Bob and Alice are using this MD5 hash algorithm. And we've inputted our first password. So we're like, the password is super common. This is what the MD5 hash is for it. What are other common passwords? What should we use for our hash table? Any suggestions? So we have password 1, and gives us this hash. So then we can go to our hash table. We can write password 1, and we can paste our thing. What other passwords would we want to include in our hash table? So we go 1, 2, 3, we get this hash, and again we add it to our table. Along the same lines, 1, 2, 3, 4, 5. It's pretty common. I can copy that. Any other suggestions? What's like 1, 2, 3, 4, 5, but with letters? Got A, B, C, D. The other one that might be pretty common is if we look at our keyboard, what are patterns with letters on our keyboard? So we have asdiff. And then the other one we had was QWERTY. Any other suggestions from Calgary? Sometimes like people's favorite shows can be pretty common passwords. And in general, like this is super slow for us maybe, but you give it a computer, you look at a database of the top 1,000 passwords, and it can make a hash table for any of your hash algorithms like very quickly. Oh, your birthday, so my birthday is December 12th, so we get that hash. Nice. So you have a nice little hash table going on here. And so say Alice does a similar thing. She starts to build this big list, and then she looks in the data that she's got, and she sees that, oh, look, I found Bob. His email paired with his password. So we can look here, and this one didn't copy properly because we see those two duplicate ones. The bottom one's supposed to be different. Yeah, so we look at this, And we look down our list and we can see it matches with this one here. And so that was QWERTY. So we think, okay, Bob's password is QWERTY. We can now get into his StringCan website authentication as him, but we know people repeat their passwords. So Eve thinks like, I'm gonna try and use Bob's email and this QWERTY password in all of his other things. She gets successful. For some reason, Bob has chosen this extremely easy password for both his new startup and for his banking information. She gets into his bank and she gets some money. So what was the counter to this? We've used it, we mentioned it. What would be the counter to this hash table? Yeah, it's salts. So there could be an argument here that like, oh, it's not my job as an application developer to protect people who have like super weak passwords. Like they should make better passwords themselves. Because with hash tables, weak passwords are vulnerable, but strong passwords are not. There's just not enough time for someone to make a hash table with like all conceivable passwords. The longer my password is, the like increasingly like infinitely small percentage chance that someone has a hash table with my password in there. If I have an 8-character password, it just gets, impossible. But for simple ones, yeah, hash tables, they're very vulnerable. And to solve this like vulnerability for people with weak passwords, we can use Assault. So Assault, when I am using this, I use the same MD5 hash, but onto anyone's passwords, I add Assault, which is like a random string. So I can go, and it's a long string of numbers, and I get this hash. Instantly, my hash data is way more secure. If I have a password database that has everyone's passwords plus this string run through the database, no one out there has made a hash table with this string attached to the common passwords, because why would they? It doesn't make any sense. They would have to do all the most common passwords and then start adding on just a bunch of random strings to like, oh, maybe I'll hit someone's salt. Doesn't happen. This, however, can be vulnerable if I'm using one salt for every password in my database. There's like a password, or there's a data breach. If someone gets all of my database plus they know the single salt that I'm using, they can make a custom hash table for my website. The way they get around this is, and I think you saw this with bcrypt, you're not adding a string with bcrypt. It says something like your password, comma, a number. And that means generate a salt of 14 characters, and that salt is different for each password in the database. So even with a very basic password, the salt is going to be dynamic for that password. And then someone enters the other basic password, we get another dynamic salt for that. So now, even if someone breaks into my database and they know I use a salt, they can't make a salt or a hash table with my passwords plus a single salt, because I'm using, a different salt for every single password that goes in. It becomes much more secure and hard to break. Although the random salt that gets generated attached to each password, like that has to come from somewhere, and it also has to be remembered. So what a lot of things do is they use a pseudo-random number generator, and this generator will produce the same series of random numbers or random strings given the initial seed. So if I say num generator and I give it a seed, it just initial thing to like give the random thing, it'll produce maybe 1, 2, 3, then 3, 4, 5, then 5, 6, 7, and it'll go infinitely, and it'll be a new random number each time. But if then someone else uses the same number generator and they use my same seed, JSKDF, they'll get the same series of random numbers. If they use a different seed, it'll change the series that they get. Yeah. disperse the crumbs in between the original password characters. So up here, I was saying that we had password and then plus the salt. And I think the question is whether, does it look like this? Like, does it concatenate it on the end, or does it like give a combination of like JSK and then the A from the password, DLF, and then the S's, so that it's like a big jumbled mess? Yeah, that's another way of, just correct me if I'm wrong, Kate, in assuming that's what you're asking. That is one way that the salt is like mixed in with the password. It depends on the different implementations. You know, you could just add it to the end, but the plugins or the modules that you're using that like bcrypt and things are probably intermixing it like this. I'm not sure exactly with bcrypt, to be honest, though, but that is another way. Yeah, so the comment was that it shouldn't really matter because there's no correlation between the input and the output. Like, we can't go reverse. And that is like huge majority true. The I guess advantage would be, again, if this thing I'm showing here, there always is some way to break something. Like, the idea is you can't be 100% secure, and if someone somehow knows my random number generator, knows the like seed that I started with, knows like which password was the first starting password, then you just, if we crumb it, if we break it down into the thing, there's just like extra levels of security. The more kind of wrenches we throw in the system for someone to be able to make a credible hash table, the kind of better. But yeah, like, it's, unless you're being very very oblivious with how you're storing, your salts or what tools you're using, you're pretty good. Okay. So finally, after all these things, they put out a notice for all the users to, refresh their passwords. They let everyone know that there was this password leak, and they added a salt onto all of their hash passwords. Bob just had a frustrated call with his bank over how easy it was for Eve to take his money. He's like, why? Just because she like got my password, why is she able to go and like to take all my money? He doesn't want it to be that easy for someone to log into StringCan, even if they have the correct password. So he's like, I don't like this experience I just had. How can I make StringCan more secure? So what can he do? Any ideas for how he can make StringCan a little more strenuous than, just having to put in the password? Or what are some things maybe we've seen when we've been using other applications out in the world that are extra steps for authentication? Yeah, so we can use two-factor authentication or multi-factor authentication if we want to go, all out. So the different factors are different like qualities by which we can prove that it's us. So multi-factor authentication could be something something you have, or something you are. So we can think of with Google sometimes does multi-factor authentication by sending you a text. So you know your password and your email, you sign to Google, but then they're like, let's prove it's you by confirming, you have your phone. If you're really Travis, you should have your password. You should also have access to your phone. So, it's something you have. The different factors that you have available to you. This last one's something you are. Nima was telling me about like some startup where like it was with ultra secure like financial things for setting up stuff, and they had like a multi-factor authentication where you would have to like video call someone like who knew you, who could provide like proof that it was you. So like you could go crazy or whatever, but yeah, that's your multi-factor authentication. Another thing that could help with this is something like a single sign-on. So a lot of pages you see these days, or even with Compass, you're logging in with GitHub, or you authenticate with Google. There's some benefits to this. There's also some cons to this. What could be some benefits of a single sign-on service? So we don't do it ourselves. We just let Google do all our sign-ons. Yeah. So if Google gets hacked, then we're kind of screwed. We don't have any say over what they do. I guess that's a con. What are some benefits to using it? There's less room to screw it up. Yeah, we can maybe have the assumption that Google, they got a lot more money than us. And they're probably doing this right. Maybe we're assuming correctly. Maybe we're assuming wrong. We just don't have to implement it ourselves. That's maybe a big benefit. The other benefit is there's a lower barrier for entry for people using our application. Sometimes, I don't know if it's the same with you, but when I'm signing up for a new service or going to a new thing I want to use, and they'll sign up for an account, I don't really want to sign up for another thing. I gotta remember the password. I'm maybe gonna use this twice. But if they pop up, just log in with Google. I'm I have a Google account. I'll do it. I'm not as averse to signing up with Google as opposed to being a part of their whole new ecosystem. Cons, like we said, you're putting all your trust in another company. You have to assume that people who are signing up for your service have Facebook, GitHub, Google, whatever you're allowing them to do a single sign-on with. Maybe someone doesn't want to use Google, but they want to use your application. Yeah, any other benefits or cons people can think of? Oh yeah, the other, Kate mentioned back when we were doing two-factor authentication, matching a security question. So that was the what's your mother's maiden name, what's your high school did you go to questions that Eve got from Alice. So if you can prove that you have the password, but also these more personal, more unique information about yourself, you're more likely to be who you say you are. The last thing we're going to end with is just looking at Passport. And that's a middleware for authentication when you're using Node. So security and authentication can be very complex, kind of like what we've seen. And I think it's a good idea for everyone to have some knowledge of the theory behind it, of how things are working. But for the applications that we're building, we, in most cases, shouldn't be building all of our own authentication. It's a lot of work. There's a lot of room to be screwing it up. And there are a lot of third-party or modules or plug-in things that we can use that are tried and tested and actually work really well. So Passport's one of them. They have that single sign-on option, so you can just do as easy as this, passport.authenticate, and give it your poison, Google, LinkedIn, whatever you want. They have other options for authentication too. They have really good documentation. So I know for your midterms, you're not going to be using authentication for them, but for your finals and other projects where you're using, if you end up using a Node Express backend, Passport's a good option for thinking about authentication. And in general, just explore the tools that you have. There are different ways you can use other people's authentication to different levels of success. So don't think that you have to, you don't have to be Alice and Bob and spend all this time implementing all of these things. But you do want them in your application. You just don't necessarily have to make it yourself. That's everything. Any questions before we wrap things up? Yeah, thanks everyone. I'll put the notes up pretty soon. And again, I'll be around, so if any questions come up, just let me know.